Okay, come on, everybody, get a little excited. Woo!
Yeah. Okay. Awesome. Great. Thanks everyone for coming. Welcome to my presentation. This will be pipeline proving practical ZK proofs for applications and what we're doing at Hylè. So I'm Lancelot. I'm the CTO and co-founder of Hylè, and I was previously working on Brick, an NFT project in the Starknet ecosystem, which is where I discovered zero-knowledge technology, validity proofs, all that jazz. I'm Variety on X, which I still call Twitter, because I'm a boomer. It is Twitter, exactly. No. Well, this is the content of my presentation anyway, so let's talk about this. What we're going to talk about is the fact that rollups are good, but they have limitations and we can improve on them. And I'm going to tell you about some of the state-of-the-art things that we're doing with blockchains on Hylè that enable this. So rollups are good. Let's quickly go over what a rollup does. In fact, well, our definition of a rollup anyways, because these words are a bit overused nowadays. A rollup maintains state commitments on the layer 1. That's like the security guarantee and assumption. And each of the state transitions in the case of a ZK rollup is validated by a ZK proof, which makes sure that you can't have like fraud, you can't do invalid transitions, these type of things. However, usually it's permissioned. Only the layer 2 sequencer can post actual validity proofs that change the state transition, that like change the state commitments, which are usually centralized. And this is, of course, unless you have escape hatches, which as far as I can tell, none of the ZK rollups that are like general purpose have in production. And indexation is also trustless, but again, you need non-L1 actors to be able to access the information. So, next slide, please. Yeah, this basically looks like that. These are, rollups are icebergs. You got the state commitment, that's a little bit floating above the water. And then you have 90% of the thing, the whole data, which is under the water, and that's on the layer 2. I feel like I'm conducting, sorry, like this was just for simulation. Yeah, and so transitions are just proofs of state transition. Transactions are just proofs of state transitions. So you start from a green commitment, and then you have a ZK proof that takes you from the green to the blue commitment, and then another ZK proof that takes you from the blue to the red commitment. But with most ZK rollups, these are actually batches of a lot of transactions, batches of blocks even. And there are several hours between each of these state transitions because for efficiency, they need to recurse a lot, they need to batch a lot. And so that takes time. So that's the first thing. And then once you want to read the information, well, you have to go through an indexer. So you have essentially two options. You could theoretically do it on your own. It could be like user indexation, or you rely on like the rollup infrastructure. They have their own indexer. In the case of, say, Starknet, Starknet provides the state of Starknet because otherwise it just would not be very usable. But in theory, somebody could do their own indexation. I think there's actually some companies that have done that. So accessing the layer 2 state, accessing what's under the iceberg remains permissionless, but you have to have somebody doing it. It's not as automatic as on Ethereum. What's interesting is that if you don't do this with batches of blocks, but with individual transactions, you end up having something that looks a lot like what I'm calling a based ZK rollup, which isn't really an actual thing, but it's essentially the same thing, and this is like the exact same diagram for a reason. Essentially, each transaction would just be a ZK proof of a state transition, and on the layer 1, you just maintain the state commitment of your own application, and you switch, and you switch. And that's exactly like how rollups work. You can do a regular application with that. But if you want to try to do that, yeah, you're gonna have some issues because right now all of the rollups are bridged to the layer 1. So they are technically interoperable, except you have to go through bridges every time. Please enjoy my drawings. I've worked very hard on them. And each of these icebergs remains quite separated from each other and from the layer 1. So if you want to do things efficiently, you run into issues. It's difficult to compose contract calls. You have long proving times. Like I explained, you need to do batches of blocks instead of individual transactions because that takes too long. You have high latency, and it's very hard to do parallelization. One of the things that I didn't gloss over, but because layer 2s are centralized, you only have one person trying to post proofs, and so they don't have parallelization. If you try to have many users at the same time, then you run into issues. So rollups are good, but they could be better, and here's how to make them better. So first, the next slide, please. So first, composable contract calls. If you want to do composition right now with ZK proofs, you're the situation on the left. Let's say for some reason, maybe the metaverse is hype again, you want to do Tetris, but you want people to have a CryptoPunk to be able to play Tetris. What you have to do is verify inside the code of your Tetris game the code of this, the CryptoPunk contract. Sorry, this was just a gesture. This is annoying because if you want to change the identity verification that you're doing, you need to change the code of your own application. You're basically like doing boxes inside boxes inside boxes. If you want to change the innermost box, you have to open everything and swap it out. With proper composability, which is what we give you if you're using the Hylè protocol network, you can do the same independently. You'd have the CryptoPunk proof that's standing on its own, you'd have your own Tetris proof, and you just add a little bit of information inside your own proof as like metadata that you expect a proof of a CryptoPunk to exist. And you can just change that little bit of metadata. You don't need to change anything else to be able to support any kind of identity. And you can actually like even abstract it away and change the code of your application without redeploying or without relying. If the CryptoPunks update, you don't need to update your application. Obviously they wouldn't, this type of things. So that's like the solution to the first problem. The second problem, which is much more annoying, is proving time and latency. So here I have an example. This is the arrow of time, and at some point there is an auction, and at some point in the middle the auction ends. That's like the red line. Let's say you're a user and you see that auction and you want to make a bid on that. If you need to generate a ZK proof to actually validate your bid, that's going to take time. And maybe it takes so much time that by the time the proof has been generated and you can send it to the chain, well, the auction's ended, and you're kind of like, you're sad and you're crying because you didn't have enough time to do this. So that's both proving time and proving latency. They're like related, and it's annoying. The second problem is parallelization. Let's say two people see the auction at the same time and they want to make a bid on that. Except the other guy, the guy in blue, he's got a faster computer or a faster horse or whatever, and he sends his transaction with his proof to the network faster than you. So he switches from green to blue. In the meantime, you also saw the original green state commitment, and so you were generating your proof based on that state, and you want to switch from green to red. But by the time your transaction arrives on the chain, the state is now blue, and we can't do anything with that. We don't know how to switch from blue to red. We only know how to switch from green to red. So this is the issue of parallelization when you're just handling state transitions on state commitments with ZK proofs. And again, you end up being very sad because you couldn't actually commit your transaction. So the solution to this is the title of this presentation. It's finally arrived. Pipeline proving, which is in a very roundabout way, kind of like going to the restaurant. You book a table and then you can kind of come whenever, well, hopefully on time, but there's still, in this example, two people, but things happen very differently. The idea is that we split sequencing of transactions from the actual settlement, which is powered by ZK proofs. So sequencing, what that means is that, well, maybe you both just send the information about your bid on chain. You send however much you want to bid. You send, I mean, like for an auction, this might be, actually, you might want to keep it secret and send the ZK proof directly, but these are like details. So you both send how much you want to bid to the chain. There's no latency because you're not generating a proof, so we just immediately receive that, we sequence that. We know in which order your bids have arrived. And so from then on, everything is fully determined. There's no guesswork, nothing can change. So we can start working on generating ZK proofs that you could legitimately actually bid on the auction. So maybe you can prove that you have enough balance or that you had enough balance at that time. You can prove that you were authorized to do the bidding because you send a signature or because somebody else authorized you or something. And we know that first we want to go from the green to the blue state and then from the blue to the red state, even though both users originally saw the green state. And we can generate ZK proofs for both of these transactions and settle them after the auctions ended, potentially. That's fine, because what actually matters for the order of operations is the initial sequencing. So the chain will only be able to reflect the state once we settle them after the proofs, but there's no way to change things, and so essentially it's like time travel. Yeah, which is pretty neat. This leads us into what we call lean blockchain, which is what Hylè is. Essentially, basically we view blockchains as just custodians of data integrity rather than through zero-knowledge proofs. They only do sequencing, a little bit of data availability, and settlements. And with pipeline proving and native proof composability, you can get like really high performance. In theory, because it's like asynchronous, you might get like, yeah, it's in theory infinite. In practice, it's not going to be infinite, but it still could go really, really high if you do enough recursion in that like latency gap. And this is really cool because instead of the previous situations where everybody was talking through bridges to a layer 1, nowadays everybody is inside the layer 1, but everybody works like a rollup, so you can still do, you can write, Rust code and run it on SP1 or RE0, whatever, and you're already interconnected via native proof composability. So like ZK Rails, I drew some like high-speed trains because we're French. And this allows you to have a lot more flexibility than what you can do in current blockchain ecosystems. So this is like a random example and does not yet reflect reality, but you could have, at the same time, permissionless on-ramp via, say, ZK email. You can prove that you're sending some money to a custodian off-chain. And this could be like fully decentralized and would work natively with, I don't know, a fully on-chain game like the ETH Frontier project that was announced recently, where the decentralization is assured by the players. And at the same time, you could do like DeFi pooling with permissionless strategies, but those strategies are actually private because they're run off-chain and executed using ZK proofs, or really any other thing you want. Of course, you can also do the regular blockchain stuff of NFT contract, any kind of identity, smart wallets, these type of things. So this is Hylè. This is what we are building right now. We are still pretty early. We're in the development of the testnet phase. We're building a new Rust client. If you're interested in checking that out, check out our socials, Twitter, Telegram, the website. I think that QR code is for Telegram, so that it might be Twitter. This will lead you to the correct places anyways. Thanks for coming, and if you have questions, we'll be around. We have a booth today at ZK Hub and tomorrow as well.